Hello everyone and welcome to another class of ATMO 620. This is going to be, I promise you, the shortest class of the entire course. I only have, 5 slides to show to you. Today I want to talk to you about transmittance. Now, transmittance is a very simple concept, and that's why we only have a few slides. And essentially it's a measure of how much radiation is let go through a particular medium. When light is propagating through it, okay, when radiation is propagating through it. Technically, it's defined as the fraction of the spectral radiance that is leaving from one point and arriving to the next, okay? And technically, it's defined in this way as the exponential of minus the absolute value of the integral between, let's say that you're going from point S1 to S2 on a light beam, okay? This is what it looks like, okay? Obviously, if you remember how we defined optical depth, and remembering that the integral from S0 to S2 minus the integral from S0 to S1 is equal to the integral from S1 to S2, then this can also be written as the exponential of minus the absolute value of the difference between the optical path to S2 and the one minus the one to S1. Notice a couple of things. First thing is that there is indeed an absolute value, and this means that it doesn't matter if you're going from S1 to S2 or from S2 to S1, so you don't discriminate on the direction. And second, because there's a minus here, it means that this exponential is always going to be smaller or equal to 1. So it really gives you the meaning of a fraction. Now, the extinction coefficient k nu, in the very simple case in which it doesn't depend on the path, okay, just remind you this is the shape. Let's say it doesn't depend on the path, and so we can take this out, no problem, okay. And we assume k nu is positive, of course. This is the exponential of this. This quantity here, the integral of rho in ds, is a quantity that is often denoted as UA from S1, S2. Now notice what it is. This is the integral of a mass over a certain path, okay? So this is, density over a certain path. And so this is mass per unit area, and in particular per cross-section of the absorber through which the radiation is going okay? Sometimes when the density is constant, it's just, it's just defined as the length over which you're propagating. A similar concept to transmittance is that of absorptance, and absorptance is the difference is simply 1 minus transmittance, and it has the same meaning of transmittance, except that is for absorption and not for transmission. So the fraction of the radiation that is absorbed, sum of the two has to be 1. Okay. We also talk about band transmittance, which is transmittance over the average transmittance over a particular frequency, over a particular frequency band. Okay, and similarly a band absorptance. Notice that lines, as we said many times, can widen for whatever reason, okay? And when you're asked what is the width of a line, then it may not be a simple, straightforward task to do, to define that. The way we define it is to define an equivalent width or integrated absorptance, if you will, and they're defined in this way, and they're defined as the average absorptance times the frequency band that you're considering. So, suppose you have complicated transmittance that looks like this. Having something like this means that it's like substituting an average absorptance over this particular frequency band that you are considering. Okay. Also, in the case in which you have a very small amounts of absorbers, then in this case, the exponential here is pretty small because the mass is small. And so you can always Taylor expand this into this function here, simple linear function. And so the equivalent width can be computed very, very simply. Okay, remember it's 1 minus transmittance, so it's simply the integral of that. This is called weak line approximation. For strong line, the opposite regime in which there is a lot of absorption, we'll talk about strong line approximations, and depending on whether you have a Lorentz or Doppler line, this is what the equivalent widths look like. Well, this was pretty much all I had to say to you about transmittance. As usual, for any questions, please let me know. Otherwise, I will see you for next class. Thank you very much.